One of the useful things about contingency tables is that once we have a contingency table, we can use the numbers in the table to estimate any joint probabilities or any marginal probabilities. So for example, say we want to know what is the probability that someone is in management given that we know that person is a female. Now, the basic probability theory equation is that the conditional probability equals the joint probability over the marginal probability. And that might sound a bit fancy, but it's pretty obvious. All we have to do, if we're assuming that we're given female equals true, is we limit what we're looking at to the row where female equals true. And in this case, 10 of our people are female in this row out of a total of 140. So the probability that someone is management given that they're female is 10 over 140, or just over 7%. The question that sometimes arises is in business situations, we don't have the full contingency table. We just have a few scattered probabilities. And really what our task is to put this all back together to recreate the contingency table. So let's use an example here to illustrate this. You've seen this before. The scenario here is a cab's involved in a hit and run accident. And of course, there's two cabs in the city, the green, which operates most cabs, and the blue, which operates a smaller number. Now, what we have in this situation is an imperfect witness. That is, the witness is saying that a blue cab was involved in the accident, but the witness, like all witnesses, is not perfectly reliable. So what they do in this case is the court goes out and actually tests the reliability of the witness by, for example, sending around a blue cab and recording whether he records blue or green on a cold, foggy, windy night. So what they can do is collect some data, some conditional data. What is the probability that the witness records blue given that the cab was actually blue or green? And what we find is that the witness is right 80% of the time and wrong 20% of the time. And what we're really interested in is what is the probability that the cab in the accident was blue just as the witness stated. Now, this blue cab, green cab problem is famous precisely because people get it wrong all the time. Now, the way to come at this formally is to write down what we know. So for example, we have what are called some prior probability estimates. These are the base rate frequencies of taxi cabs in this town. 15% are blue, 85 are green. And what the prior probability means is that if we didn't know anything about the cab, if we didn't have any witnesses, we could say green. Green is involved in any incident, regardless of the incident. We could say green and be right on average 85% of the time and wrong 15% of the time. Then in this case we have some evidence. We have an eyewitness reporting something very specific. The witness reported blue, which I've denoted here with a small b. And then, as we said, the court's gone out and tested the reliability of the witness and determined that the probability of the witness saying blue given the car was actually blue, so that notation is small b, vertical line is read as given, and then big B, the actual event that it was a blue cab, is 80%. And the probability of the witness reporting blue cab when in fact a green cab was used during testing is 20%. And here the notation for what we're going to call the posterior probability is what's the probability that the hit and run cab was blue, big B, given that the witness reported small b. So let's construct the contingency table based on what we know. We know from our evidence that the probability that the witness reports blue given the cab is actually blue is 80%. So we can limit our attention to the row of the contingency table in which we know the cab is blue, big B. Now the evidence tells us that 80% of the time the witness will report this blue cab as being blue, so we can just simply calculate 80% times that 15 gives us 12. We can then go through the rest of the table using similar arithmetic to fill in the numbers at each cell. Then we focus our attention this time on the column in which the witness reported blue. Now, yes, the witness was often right when the cab was blue, but the witness was wrong 20% of the time. But 20% of the much larger number of green cabs is a relatively large number. So of the 29 cabs reported by the witness as being blue, assuming we did this many trials, only 12 of them would actually be blue, and this is where we get the probability of 41%. Let's do another very famous example to make sure you've got this. So let's say there's a rare but dangerous flu that's spreading, and because it's rare, the probability of being infected is only 1 in 1,000. But a new test has been developed, and this test is 99% accurate. You test positive for the flu. What does this mean for you? Again, it might not be obvious, but what we're looking for in this question is a conditional probability. The probability that you have the flu given that you have tested positive. And as before, one way to come at this is to start with a large sample. So if we take 100,000 people and we apply the base rate of this disease, 1 in 1,000, we should expect about 100 people in this sample of 100,000 to have the flu. So now if we just focus on people who have the flu, those 100 people, we should expect that given a test that's 99% accurate, 99% of those who have the flu should test positive, and only one who has the flu should test negative. That's that false negative. We can then use the same logic for the other 99,900 who don't have the flu. And because this is such a large number of people, we should expect actually quite a few false positives. That is, a positive test even though they don't have the flu. So if we focus then on the people who do test positive, we see that the vast majority are false positives, and thus the probability of having the flu, given that you've tested positive, is not as high as you might have thought. So you might be asking yourself, is there an easier way to do this without having to reconstruct the contingency table? And the answer is definitely yes, using Bayes' rule and probability theorem. But let's just take a step back and keep in mind what we're trying to do here. What I'm going to do is draw a very simple Bayesian network, which consists of nodes and arrows or arcs. So the first thing I'm interested in is the event F, which is the event in which I have the flu. Now, this is very interesting because from a gap analysis point of view, this is something I'm very, very interested in. I want to know whether or not I have the flu, but unfortunately, I cannot measure the gap. That is, my desired state of the world is not to have the flu, and my actual state of the world is unknown. I can't measure it directly. Instead, I have to use evidence or proxies. In this example, we have a very effective test, though not a perfect test, that provides evidence of whether or not an individual has the flu. So naturally, having the flu influences the outcome of this test, hence the arrow from flu to test. But the test does not influence whether or not the person has the flu, obviously. Now, once we have the Bayesian network, we can use the basic formulas of probability to calculate the posterior probability. That is, the probability of the thing I'm interested in given the outcome of the evidence. Now, of course, we don't actually solve these equations. These equations are going to be implemented in software called Bayesian network software, and the computer will do the math. The ability to solve these equations and determine these probabilities is absolutely important in gap analysis where we can't observe the variable of interest and instead have to rely on proxies or evidence. I'm going to use the Netica software to create a very simple Bayesian network to solve the flu problem. So to create one, I start off with my two nodes. And this first one I'll call flu, and my two states are, F, I have the flu, and NF, I don't have the flu. And that's okay. And then the next one, it's going to be the test, and my two states are positive and negative. So those are my two outcomes. So I set this up first with my two nodes, and then I draw the arc, or the arrow if you prefer, that connects them. Now what I have to do is go in and add my probability information. So for flu, if I bring up what's called the table, I can say, well, the probability of having the flu is 0.1%, which means the probability of not having the flu is 99.9%, 1 in 1,000. Now for test, it's a little bit more complicated because there's an arrow coming into test, which means the outcome of the test is conditional on the flu. So we'll see that with the table. It's not the best interface, I don't think, but it's okay. So the probability of giving a positive test given that you have the flu, remember, is 99%, and 99% for correct negative. And then there's a 1% of a false negative, that is a negative result when you have the flu, and a 1% chance of a false positive. The test comes back even though you don't have the flu. So I save that and I compile the network, and that's my completed Bayes network, or Bayesian network if you prefer. It's not very complicated and it doesn't tell you much. For example, up at the flu node, it simply tells you that you have a 0.1% chance of having the flu and a 99.9% chance of not having the flu. We know this already. But look what happens if we come into the test node, right-click it, and enter a finding. So if the finding comes back positive, we click that, and you see the Bayesian network updates to show us the probability of having the flu given a positive result. Let's return to this notion of gap analysis in order to illustrate a more complicated and a more useful Bayesian network. So always before in gap analysis, we're interested in the desired state of the world, the actual state of the world, and the gap between those two states, which creates creative tension, or more practically, the trigger for your managerial action. Now, in the case of lung cancer and x-rays, the desired state of the world is clearly not to have lung cancer. But the actual state of the world is unknown. It's costly or painful or both to find out for certainty whether an individual has lung cancer, and thus we have to rely on evidence and conditional probabilities to make a better informed assessment. Here we have a more complicated Bayesian network, but it's exactly the same as the simple Bayesian networks we saw previously. There's nodes that reflect probabilistic outcomes, true or false, and there's arcs that show probabilistic relationships. At the center of this is what we're interested in, which is whether or not the patient has lung cancer. Now, what we have at the top of the network is what the modeler here has called contributing factors, things that influence the probability of lung cancer. And what we have at the bottom of the network is symptoms of lung cancer. That is, observable things that are caused by lung cancer. Now, the network's a little bit more complicated than this because lung cancer shares some contributing factors and some symptoms with other diseases. So, for example, lung cancer, tuberculosis, and bronchitis can all cause dyspnea, which is just shortness of breath. Alternatively, lung cancer and tuberculosis can cause an abnormal X-ray result, although the abnormal X-ray results don't obtain with mere bronchitis. On the other side, smoking can influence the probability of both lung cancer and bronchitis, but world travel influences the probability of getting tuberculosis. Now you might ask, why is tuberculosis of interest here? Well, tuberculosis is an alternative cause for an abnormal X-ray or shortness of breath. So tuberculosis is important in the extent to which it explains away the symptoms. So this is all extremely complicated. And what we do with Bayesian networks is two things. We use the network to structure the relationship between, say, these contributing factors, the things we're interested in, and the symptoms. And we use it to keep track of the contingency tables or the conditional probabilities we require to do the mathematics to update the probability. Now, the probability that we're interested in this case, is what's the probability of lung cancer given world travel, given smoking, given X-rays, given shortness of breath. Put it all together and give us the best possible estimate of the probability of lung cancer. So let's look at how this Bayesian network functions. As before, if we click on any node and look at the table, we see that the network embeds conditional probabilities. So in this case, it's the probability of having tuberculosis given world travel. So if you visited somewhere, there's a 5% chance of getting tuberculosis, and if you haven't visited, sort of a 1%. Now all this data is made up, so don't worry too much about that, but it gives you the idea that you can enter in conditional probabilities. Some nodes, like the dyspnea one, we actually have two arrows coming in, which means the conditional probability is a bit more complicated. We have two variables, tuberculosis or cancer on one hand and bronchitis on the other, and we can see the extremes. If tuberculosis or cancer is true and bronchitis is true, then there's a 90% chance of shortness of breath. Whereas at the bottom, if tuberculosis or cancer and bronchitis are absent, there's only a 10% chance of shortness of breath. So how does this Bayesian network actually work in practice? Well, imagine someone comes in and says, I have a symptom. People just don't come into the doctor for no reason. So let's take the symptom and enter a finding and change the probability of dyspnea from its baseline to 100%. The person's coming in and saying, look, I have shortness of breath. I'm certain. Now notice right off the bat, this changes the probability of lung cancer from 5% to 10%. It doubles the probability of lung cancer. So the next thing you do if you're a physician, definitely not cut the person open to see whether they have lung cancer, but maybe do some simple things. In fact, I wouldn't even do an X-ray at this point because X-rays are costly and have some risk. Next thing you'd probably do is ask some questions about contributing behaviors. So for example, does the person smoke? And if the person says yes, and I enter that finding, the probability of smoking is 100%, which brings up the probability of lung cancer, again, quite a bit. Although the probability of of bronchitis is much higher. So at this point, it looks like bronchitis. We may also ask about world travel. Now notice what happens when I hit world travel and I say there was a visit. My probability of lung cancer drops ever so slightly. And the reason it drops is because the probability of tuberculosis goes up. If there's no visit, then the opposite happens. The probability of tuberculosis goes down significantly, and lung cancer goes up a little bit. At this point, we have about almost a 15% chance of lung cancer. It might be worthwhile to do the chest x-ray. So if the chest x-ray comes back abnormal, then we definitely have a problem. We definitely have evidence of a gap in terms of lung cancer. There's a 72.6% chance that this person has lung cancer. Still a pretty solid probability of bronchitis, but lung cancer looks pretty likely. If, on the other hand, the x-ray had come back normal, then you see the outcome, the cause of shortness of breath is almost certainly bronchitis, and lung cancer is a bit of a long shot. So this is how a Bayesian network can be used to combine evidence and information from multiple sources to update or improve a conditional probability estimate, which in this case becomes a tool for gap analysis, for noticing or deciding whether or not a person might or might not have lung cancer.